Okay, in this new chapter on atomic structure and the periodic table, you will learn how to draw and label a model of an atom, as well as interpret models of atoms, distinguish between atoms, ions, and isotopes, describe the organization and the arrangement of the elements on the periodic table, look at the categorization of elements as metals, nonmetals, and metalloids, and describe and differentiate between them based on their properties and locations on the periodic table, and use the periodic table to help distinguish between atoms by determining the numbers of protons, neutrons, electrons, and describe a bit about the arrangement of the electrons. You will also be able to record the identity of an atom using notations such as the hyphen notation and nuclear notation. Let's look back and review and remember that matter is anything that has mass and takes up space. All matter is made of elements, and elements are further made of atoms. Atoms will be the smallest unit of an element that retains the properties of that element. It took a lot of time, many scientists over thousands of years, to get to today's understanding of the atom. And the model of the atom has had to change as we've learned new information and new technology has become available. Our first understanding or idea of the atom started way back in 400 BC with Democritus, who was a Greek philosopher. His ideas of atoms weren't really believed, and it was left alone until Dalton came back in the early 1800s and gave us a solid spherical model of the atom. In the early 1900s, through the work of Thomson and Rutherford, we learned that there was a nucleus and protons and that electrons had negative charges. Bohr and Schrödinger further worked on the arrangement of the electrons and gave us a better understanding of the electron cloud. We're going to start with the basics of atomic structure. The atom is composed of 2 regions and 3 subatomic particles. The 2 regions are the nucleus and the electron cloud. In the nucleus are 2 subatomic particles, the proton and the neutron. Protons are positively charged and have a mass of 1 AMU, or atomic mass units. Neutrons are of equal mass with 1 AMU, but they have no charge. They're neutral. Because the nucleus contains 2 particles with equal mass, they make up most of the mass, or 99% of the atom. The mass number is a representation. Sorry, my dogs are barking and my kids were yelling. The mass number represents the mass of a single atom found by adding the number of protons and neutrons. Outside of the nucleus, we have an area called the electron cloud. That's where we will find the electrons. Electrons are small, negatively charged particles. They're so small, it's not that they have no mass, but compared to the mass of a proton and neutron, they are assigned a mass of 0 AMU. There are some electrons that are of particular importance. Those are called valence electrons. These are electrons that are located in the outermost energy levels in the electron cloud. The electron cloud is going to be responsible for the volume or size of the atom. Just a note on atomic mass units. They're used because some atomic particles are so small and not practical or able to be measured in grams, so we use the measure of atomic mass units. An atomic mass unit, you can see, is a very small portion of a gram, 1.61 times 10 to the negative 24th grams. Here's a model of an atom. This is a Bohr model of the atom. You can see the center of the atom, the nucleus with the positively charged protons and the neutrons with no charge. We can see the electron cloud is the region outside the nucleus, and you can see that those electrons are dispersed within the electron cloud into areas we call energy levels. The current model of the atom is called the quantum mechanical or electron cloud model. This was Schrödinger's model of the atom that was determined through very complicated physics formulas and equations, looking at the probability of finding electrons in certain areas within that 3-dimensional space we call the electron cloud. Because of its complexity, the Bohr model is often used as a simple model that shows us protons and neutrons in the nucleus, and it shows us electrons distributed in the electron cloud in energy levels. As we draw and use the electron cloud and energy level model from Bohr, we can note that the energy level 1 is closest to the nucleus, smallest in size, and lowest in energy. As we discussed atomic structure, there are two particles that are charged, the proton with a positive charge and the electron with a negative charge. These two oppositely charged particles are attracted to one another, just like opposite ends of a magnet are. We call this attraction electrostatic or Coulombic attraction. This is that force of attraction between oppositely charged particles, and again, within the atom, this is the proton and the electron. Because atoms are electrically neutral, these charges need to balance each other out, so there's a net charge of 0. That would mean that the number of protons would have to equal the number of electrons. So again, that net charge would be 0 and there would be no overall charge. My head is blocking the image, but if the charge of 2 protons is positive 2, charge of 2 neutrons is 0, the charge of 2 electrons is negative 2, and again, that net charge for a helium atom would be 0. As we look at trying to differentiate one atom from another, the atomic number is very important. The atomic number indicates the number of protons found in the nucleus of the atom. In the model to the right, the nuclear notation, you can see that it's written in the bottom left-hand corner, and it's denoted with the symbol Z. The number of protons in an atom is unique to its element, and it's used to identify. If you change the number of protons, you change the identity of the element. You can see in the faceplate at the bottom of the image here that the atomic number is written in the top square on your faceplate on the periodic table. And if you moved throughout the periodic table, you could see that each element has a different atomic number and that the periodic table is organized by increasing atomic number. You will now use your periodic table. So pause this video and take out your periodic table and complete the chart below. The first one has been done for you. So if you see the element lithium, you find it on the periodic table. It's in group 1, the first column on the periodic table with symbol Li. Notice that the element symbols are written as the first letter is capitalized and the second is lowercase. Please be careful when writing the element symbols. The number above the symbol for lithium is the atomic number. It is 3. The atomic number tells you the number of protons. And in neutral atoms, remember that in order to have a net charge of 0, the number of protons must equal the number of electrons. So with 3 protons, 3 positive charges, there would also be 3 electrons and 3 negative charges. Please complete this table for boron, argon, and magnesium. Pause the video, and I will reveal the answers on the next slide. Here you go. Here are the answers. I hope you've gotten them all correct. Again, remember with boron, we find boron element B. The atomic number is 5. The atomic number tells you the number of protons, so the number of protons is 5. In a neutral atom, if there are 5 positive protons, there must also then be 5 negative electrons, so the atom is neutral and the net charge is 0. The same applies for both argon and magnesium. Isotopes. Isotopes are atoms of the same element with different mass numbers due to different numbers of neutrons. Oftentimes, when we're dealing with elements, we're not dealing with single atoms of an element, we're dealing with larger samples. And within a larger sample of an element, you'll notice variations. Those variations are called isotopes. These isotopes will differ in their masses because there's a variation in the number of neutrons for each atom. Isotopes will have the same chemical and physical properties. They will contain the same number of protons and have the same atomic number. They will have different neutrons and different mass numbers. Some isotopes will be more abundant or common in a sample than others, and some isotopes are not stable in their nucleus and they will decay over time. These are called radioisotopes. The picture in the image below shows 3 isotopes of hydrogen. You can notice that in the nucleus, they each only have 1 proton. You can see that hydrogen 1 here has 1 proton. Hydrogen 2 has 1 proton and 1 neutron, giving a mass of 2. And hydrogen 3 has 1 proton and 2 neutrons, giving you a mass of 3. You can notice that each of them have only 1 electron in the nucleus, as they are all neutral. So 1 proton with 1 positive charge would relieve 1 electron, 1 negative charge. Because of these variations, we have to have notations that will allow us to distinguish one from the other. These notations represent the mass number and the atomic number and the element symbol in the nuclear notation. The other notation is called a hyphen notation. This notation only has the element name or symbol followed by the mass number. Remember, the mass number is specific to the mass of that atom, and when we calculate the mass number, we add protons and neutrons only. We don't include the electrons because they are so small. It's like they have no mass at all. That would be if I got on the scale and wanted to take an earring off to get my weight on the scale. That earring's not going to move the needle, so it's not necessary to remove. Here's the nuclear notation, and that's our hyphen notation. So in summary of atomic structure, we have protons with a positive charge and a mass of 1 located in the nucleus. We have neutrons with no charge, they're neutral, also with a mass of 1 located in the nucleus. We have electrons, those are the small particles in the region outside the nucleus we call the electron cloud. They have a negative charge, and they're so small that they're assigned a mass of 0 AMU. Also, in summary, to determine the number of protons, neutrons, and electrons. To determine the protons, we look at the atomic number. To look at the electrons, we would look at the number of protons for a neutral atom. To determine the number of neutrons, we would have to take the mass number and subtract from that the number of protons, which is the atomic number. Okay, your turn to try some practice. Again, I'm going to have you pause the video. Find nitrogen, fluorine, and potassium on the periodic table. I've given you the hyphen notation. Remember, in the hyphen notation, I've given you the element symbol followed by the mass number. For carbon 13, the 13 is the mass number. The mass number is not on the periodic table. It is the mass of that single atom by adding its protons and neutrons together. In the second column, you can see the nuclear symbol or the nuclear notation. The 13 in the upper left corner represents the mass number, and the 6 down below represents the atomic number. Those are both filled in the table. To find the number of protons, I look at the atomic number. To find the number of electrons, I look at the number of protons. And to find the number of neutrons, I find the difference between the mass number and the atomic number. The mass number is protons plus neutrons. When I take away the protons, I'm left with 7 neutrons. Please pause the video and complete the 3 problems below. Here are the answers. Please look through them. Pause the video as you review them. Not all atoms are neutral. Sometimes we have a gain or loss of electrons and resulting in an ion. An ion is an atom with an unequal number of protons and electrons. The formation of ions involves only the change in the number of electrons. If you change the number of protons, you would change the identity of that element. So it's formed due to the gain or loss of electrons. We have 2 types of ions. We have a cation. This is an ion with a positive charge due to a loss of electrons. A nice way to remember it is the T in cation looks like a plus sign. We also have an anion. So when we gain more negative electrons, we have an overall net negative charge. So this is an ion with a negative charge due to gaining electrons. And another trick to remember this is that the N in anion stands for negative, a negative ion. You can see in the image down below, there are 3 images. There's a neutral atom in the beginning of carbon with 6 protons and 6 electrons. There is a negatively charged carbon anion in the middle with 6 protons and 7 electrons. So there's 1 extra negative electron. And there's a positively charged carbon cation on the right. You can see that it has 6 protons and has lost 1 electron, 5 electrons. So there's a net positive charge of 1. Atoms will form ions to increase stability. This has to do with the arrangement of the electrons within the energy level, specifically with those valence electrons, the electrons that are in the outermost energy level. In general, atoms with fewer than 4 valence electrons, those are your metals, will tend to lose electrons and form cations, and atoms with 4 or more valence electrons will tend to gain them. Those are your nonmetals. We have a rule that talks about that. That's called the octet rule. So elements are most stable when they have 8 valence electrons. And there are patterns within the periodic table that help us to predict those. We can see that the elements in group 1, the first column on the periodic table, because they have the similar 1 valence electron, they will all lose 1 electron. Due to the loss of an electron, they will form an ion with a +1 charge, a cation. The pattern continues for metals with positive charges and changes when we get to nonmetals. A nonmetal in group 16 with 6 valence electrons will gain 2 electrons to fill the octet and form an ion with a -2 charge. There is one exception to these trends. Helium in group 18 has only 2 electrons, has only 2 valence electrons, and therefore will only have those 2. The noble gases in group 18 will not form ions because they already have a stable electron arrangement. The transition metals in group B from the periodic table are omitted from this conversation as their electron structure is a bit more complicated and they don't always follow patterns as represented by the group A elements. Again, you've had some familiarity with looking at the face place to determine protons, neutrons, and electrons. Just remember that when we look at element symbols, that the first letter is always capitalized and the second letter is lowercase. Element symbols are based off of 1 or 2 letter symbols. Some of the symbols don't seem to match the element name. That's because some of the elements were discovered back when they were speaking Latin or German or Greek, and so those names are from that base language. Also, from your color-coded periodic table, you have identified that the periodic table is arranged by increasing atomic number. This is through the work of Mendeleev and Moseley, who discovered properties that repeated themselves when they organized the periodic table thus. The periodic law is a very important law in chemistry that identifies that when the elements are arranged by increasing atomic number, not in order of their discovery, not in alphabetical order, that there will be a repetition of their properties. This helps us to make predictions and use the periodic table. The periodic table is organized into vertical columns called groups. Groups are also called families because elements placed in the same group share specific and similar characteristics. The groups are numbered 1 through 18, and some of the groups have specific family names. Group 1 is called the alkali metals, Group 2, the alkaline earth metals, Group B, the transition metals, Group 7A or 17, the halogens highlighted in green, and Group 18, the last column on the periodic table, or 8A, are also called the noble gases. Periods are horizontal rows on the periodic table. There are 7 horizontal rows on the periodic table. The 2 spaced at the bottom and separated from the periodic table are called the lanthanide and actinide series. They are also called the inner transition metals, and they fit into the periodic table after elements 57 and 89, and they were pulled out and placed below for space-saving purposes. We can categorize elements on the periodic table as metals, nonmetals, or metalloids. Metals make up 80% of the elements, and they're found on the left side of the periodic table all the way to the staircase, with the exception of hydrogen. They have some similar characteristics or properties. Metals are shiny or lustrous. They're good conductors of heat and electricity. Most of them are solid at room temperature, with the exception of mercury, which is a liquid. They are malleable, that means they can be hammered into sheets, or ductile, which means they can be drawn into wires. Nonmetals are located on the right side of the staircase, plus hydrogen. They have more variation in their state at room temperature. Many nonmetals are gases at room temperature. Bromine is a liquid, and some, like carbon, are solids, but however are brittle and not shapeable, like the metals. They tend to have properties that are opposite of the metals and are poor conductors of heat and electricity. There's a special group of nonmetals called the noble gases located in group 18 of the periodic table. The last category of elements is a small group of elements that are located physically between the metals and the nonmetals on the bold staircase on the periodic table. Those are called the metalloids, and they have properties that don't fit quite neatly as a metal or a nonmetal, characteristics of both. Here you can see where they're located. Again, keep in mind that hydrogen is that exception. It's located on the top left of the periodic table. However, it is not an alkali metal. It is a nonmetal. You can also use the periodic table to help you predict arrangement of the electrons. If you know an element's location on the periodic table, you can predict its arrangement of its electrons and several other properties as well. In general, atoms of elements in the same group will have the same number of valence electrons. An example of this can be seen with the alkali metals, lithium and sodium in group 1. Both of these elements have one valence electron. Again, both of these elements will lose that one valence electron and form ions with a positive 1 charge. Note that this trend is applying for the group A or representative elements only. Again, the transition metals in group B have a lot of variation in their trends. As you move from left to right across a period, the number of valence electrons will increase from 1 with the alkali metals in group 1A to 8 with the noble gases in group 8A. The periods or horizontal rows on the periodic table also give us some information about the electron cloud. It corresponds to the number of energy levels that the electrons are distributed in within the electron cloud. As you move down a group, the number of energy levels will increase. Here are a couple images that display that. The top right corner talks about the ion charges, and you can see the patterns from the metals losing their valence electrons and forming positive ions on the left side of the periodic table to the nonmetals gaining valence electrons to fill their octet. And the noble gases with their full octet not forming ions. The bottom table shows the number of valence electrons. Remember that helium is an exception on the noble gas column because helium only has 2 electrons and therefore has 2 valence electrons.